a pale blue-green world, distant, frigid, and seemingly uneventful. For a long time, that was how we believed we understood Uranus, the ice giant discovered by William Herschel in 1781. But modern observations and Earth-based telescopes have revealed massive storms, bright methane clouds, and extraordinarily powerful seasonal atmospheric changes. In reality, Uranus is one of the strangest planets ever discovered. Its rotation axis lies almost sideways relative to its orbital plane, creating energy variations unlike anything seen elsewhere in the solar system. Even more remarkable, the planet's magnetic field is profoundly unusual, offset by about 59 degrees from its rotation axis. We were wrong about Uranus. And today, we begin that journey again. On the 24th of January, 1986, the spacecraft Voyager 2 swept past Uranus at its closest distance, just over 81,000 kilometers above the cloud tops. It remains the only time humanity has ever visited this planet. Nearly everything we have known for almost 40 years about its atmosphere, magnetic field, and weather has come from only a few hours of observation during a single flyby in an orbital cycle that lasts 84 years. Yet there was one crucial detail. We saw it at the wrong moment. In 1986, the south pole of Uranus was pointed almost directly toward the Sun. When Voyager 2 arrived, the southern hemisphere was deep in a decades-long summer, while the northern hemisphere was nearly buried in total darkness. The images sent back to Earth revealed a pale green sphere, smooth and almost featureless, with barely any visible cloud structure. There were no swirling cloud bands like those of Jupiter, no gigantic dark storms like those seen on Neptune. But as observational technology advanced, space telescopes began to uncover a very different story. Since the late 1990s, the Hubble Space Telescope has monitored Uranus across multiple seasons. Especially after the 2007 equinox, atmospheric activity began to increase noticeably. Bright methane clouds appeared more frequently, wind systems shifted, and convective structures became clearer. Images captured by the James Webb Space Telescope in 2023 show a dense luminous ring surrounding the northern polar region, believed to be caused by the long-term accumulation of photochemical aerosols under prolonged sunlight. Meanwhile, the South Pole is beginning to darken as it enters a winter that will last for decades. This reveals something essential. Uranus is not quiet. It simply changes on a rhythm far slower than human patience. Infrared data indicate that temperatures in the upper cloud layers fluctuate around -214 degrees Celsius to -224 degrees Celsius, yet the distribution of heat varies between seasons. As sunlight shifts along the planet's 84-year cycle, the structure of high-altitude winds changes as well. Wind speeds can exceed 250 meters per second at certain latitudes, nearly 900 kilometers per hour. And if a single poorly timed glimpse can lead us to misunderstand an entire planet, what might we discover when we finally explore the true structure hidden beneath those pale green clouds? If we observe the solar system from a distance, most planets spin like slightly tilted tops. Uranus, however, is entirely different, as its rotational axis is tilted by 97.77 degrees relative to its orbital plane. That means it is almost lying on its side as it moves around the Sun with such an extreme tilt. Its poles alternately point almost directly toward the Sun during different phases of its orbit. For decades at a time, when one hemisphere remains continuously illuminated, solar energy accumulates in the upper layers of the atmosphere. Solar energy accumulates in the upper layers of the atmosphere. As the planet approaches an equinox, temperature differences begin to trigger powerful convection. Massive streams of gas move at speeds of hundreds of meters per second, creating a global circulation system unlike that of any other planet. Instead of the parallel cloud bands seen on Jupiter, Uranus tends to form seasonally symmetric structures. When a pole is exposed to sunlight for many years, photochemical reactions occur in the upper atmosphere, generating aerosols and altering the way sunlight is reflected. The 97.77 degrees axial tilt does not affect only the climate. It also influences the entire ring system and its moons. Uranus's rings orbit almost exactly along its equatorial plane, meaning they too appear nearly upright relative to the planet's path around the Sun. Such an extreme tilt is difficult to explain through ordinary planetary formation processes alone. Several hypotheses suggest that in the early history of the solar system, roughly 3 to 4 billion years ago, Uranus may have experienced a colossal collision with a celestial body several times the mass of Earth. And with an axis that lies almost sideways, the distribution of sunlight becomes even more extreme. One half of the planet can remain in continuous daylight for nearly 4 decades, while the other half sinks into the deep darkness of space. when internal energy is weak and external sunlight is distributed in such an extreme way. What might be happening deep beneath those pale green clouds? We will look further into the mystery of Uranus's internal heat and the possibility that the planet itself may be the fossilized remnant of an ancient planetary catastrophe. Before you stands Uranus, a pale green world, strangely quiet. Yet the feature that has puzzled scientists for nearly 4 decades is not its color, but its cold. The lowest temperature ever recorded in the cloud layers of Uranus is about -224 degrees Celsius. This makes it the coldest planetary atmosphere in the solar system. It is colder even than Neptune, despite Neptune being farther from the Sun. In planetary physics, excess internal energy usually comes from residual heat left over from formation, from gravitational contraction, or from radioactive decay. Giant planets such as Jupiter and Saturn radiate significant internal heat. So Uranus appearing so thermally inactive is highly unusual. Classical interior models suggest that Uranus contains a rocky core surrounded by a thick layer of ices consisting of water, ammonia, and methane under extreme compression, with an outer envelope of hydrogen and helium gas. Temperatures in the core may reach roughly 5,000 degrees Celsius, while pressures at the base of the mantle are estimated to approach 600 gigapascals. And with such a structure, it should not have cooled so quickly. So what happened? One leading hypothesis emerges from dynamical simulations. Around 3 to 4 billion years ago, during the chaotic early era of the solar system, Uranus may have collided with a celestial body 2 to 3 times the mass of Earth. The impact may have occurred at an oblique angle, powerful enough to disrupt the planet's internal structure without destroying it. Instead of efficiently transporting heat from the core outward, the altered layers may have acted like a colossal insulating blanket. Heat became trapped deep inside, unable to escape to the surface, leaving the planet hot in its interior while appearing cold on the outside. What makes this idea particularly intriguing is that it may explain not only the weak heat flow but also the planet's extreme axial tilt. What we possess instead is a brief flyby dataset from Voyager 2, along with spectroscopic observations from telescopes such as the Hubble Space Telescope and the James Webb Space Telescope. From these fragments of evidence, scientists build numerical models and compare them with other planetary systems. Some recent studies also suggest that chemical layering inside the planet may suppress large-scale convection. If the mantle does not mix vigorously, Heat cannot rise efficiently toward the surface. It does not lack energy. It simply cannot release that energy effectively. Under pressures of millions of atmospheres and temperatures of thousands of degrees, matter no longer behaves the way it does on Earth. It enters exotic states that we can reproduce in laboratories only with extremely powerful lasers. These conditions force scientists to reconsider how planets form, evolve, and separate into layers. If a single collision can alter both a planet's rotation axis and its internal heat transport for billions of years, then perhaps even the term ice giant deserves to be reconsidered. For many decades, Uranus has been classified as an ice giant. The name seems straightforward: a large planet composed primarily of frozen water, ammonia, and methane. But in planetary science, the word ice does not mean the familiar blocks of frozen water we know on Earth. It exists in phases of extreme compression and intense heat, far beyond everyday intuition. Classical structural models suggest that Uranus contains a silicate metal core at its center, surrounded by a thick mantle layer composed of ices such as water, ammonia, and methane in a highly compressed liquid state. Yet we have never directly measured the internal structure of Uranus. Everything is inferred from gravitational models, average density calculations, and the limited data gathered during the Voyager 2. With a mass about 14.5 times that of Earth and a diameter of 51,118 kilometers, Uranus has an average density of roughly 1.27 grams per cubic centimeter, higher than pure hydrogen, helium gas, but lower than rock. Recent simulations of interior structure raise an intriguing question. What if the proportion of rock inside Uranus is higher than we once believed? Some models suggest that the ratio of rocky material to water could vary widely, possibly even reaching levels where rock becomes the dominant component. In the standard model of solar system formation, ice giants like Uranus and Neptune first accumulated rocky cores and only afterward gathered layers of ice and gas, while sufficient material still remained in the protoplanetary disk. Under conditions of extreme pressure and temperature, laboratory shock compression experiments using powerful lasers have shown that water may enter a state known as superionic ice, where oxygen atoms form an almost solid crystal lattice, while hydrogen protons move freely through it like a liquid. Matter in this state behaves partly like a solid and partly like an electrically conductive fluid similar to liquid metal. In other words, we are describing a world where matter behaves in ways entirely different from anything familiar on Earth. Observations from the James Webb Space Telescope now reveal cloud structures and methane distribution in greater detail than ever before. Infrared spectra refine estimates of atmospheric composition, allowing scientists to place tighter constraints on models of the planet's interior. What is truly remarkable is that Uranus may not be unusual at all in the broader universe. Most exoplanets discovered so far are roughly the size of Neptune or slightly smaller. If the internal structure of Uranus is more complex than expected, the consequences may appear elsewhere in the way the planet generates and maintains its magnetic field. But if the conductive layer does not lie at the core as it does on Earth, but instead exists in an off-center, asymmetrically layered region, what kind of magnetic field would such a world produce? When Voyager 2 flew past Uranus in January 1986, it did more than take photographs. It carried a magnetometer and detected one of the most unusual magnetic field structures ever recorded in the solar system. On Uranus, the magnetic field is tilted by about 59 degrees relative to the planet's rotation axis. Even more striking, the center of the magnetic dipole is offset from the planet's center by nearly 1/3 of its radius. But its structure is far from a neat, simple dipole. As a result, the shape of the magnetosphere becomes distorted and changes dramatically with each planetary rotation. And Uranus rotates rapidly, about 17 hours, 14 minutes, and 52 seconds for one full rotation. According to updated analyses, based on historical data and modern observations, each time the planet spins, its tilted magnetic field sweeps through space like a misaligned lighthouse beam. The result is that the magnetosphere becomes twisted into a corkscrew structure, a spiral stretching millions of kilometers behind the planet in the direction of the solar wind. Magnetic field lines become unstable, continuously compressed and stretched. This is the electrodynamic environment surrounding Uranus, a system that is asymmetric and constantly shifting from hour to hour. Interior models of Uranus suggest that the planet's electrically conductive layer may not lie within the central core, but instead in an intermediate mantle region where water, ammonia, and other compounds exist in supercompressed or superionic states. Reanalyses of the data in the 2020s suggest that Voyager 2 may have passed Uranus during an unusually strong episode of solar wind that compressed the magnetosphere. On Uranus, infrared and ultraviolet observations from the Hubble Space Telescope show that auroras do not remain fixed at two clear geographic poles. In 2023, infrared observations recorded auroral emissions that did not fully align with the predicted positions of a simple dipole field. If electrically conductive material exists at intermediate depths, and if superionic water truly forms powerful electrical currents, then the dynamo inside Uranus may operate within a geometry entirely different from that of Earth. Is the atmosphere of Uranus truly as calm as it appears? Or beneath those quiet clouds lies a world whose dynamics move slowly yet with far greater intensity than we once imagined? The atmosphere of Uranus is composed primarily of hydrogen and helium, with about 2% methane. It is methane that strongly absorbs red light while reflecting blue-green wavelengths, giving the planet its distinctive color. Spectroscopic and infrared measurements reveal a clearly layered structure. A troposphere below, a stratosphere above it, and higher still a thermosphere where temperatures can exceed 500 K due to the absorption of radiation and interactions with high-energy particles. These winds flow along lines of latitude, forming atmospheric bands, although they appear far subtler than those seen on other giant planets. Then in 2014, something unexpected occurred. Observations from the WM Observatory recorded the brightest storm ever seen on Uranus at a wavelength of 2.2 microns. In infrared images, a massive cloud suddenly flared into view, reflecting nearly 30% of the planet's total reflected light at the time of observation. Long-term observations from the Hubble Space Telescope and more recently the James Webb Space Telescope reveal variations in brightness across different latitudes. The formation of high-altitude methane clouds and the appearance of smaller vortex systems. What drives these storms? At greater depths, methane can condense into ice crystals when temperature and pressure conditions become favorable. This condensation releases latent heat fueling convection in a process similar to thundercloud formation on Earth, though on a planetary scale. Atmospheric models suggest that these convective cells may penetrate multiple atmospheric layers, carrying material upward from deep below. In addition, the interaction between Uranus's offset magnetic field and its upper atmosphere may generate chemical disturbances. High-energy particles from the solar wind travel along magnetic field lines and collide with molecules in the thermosphere, producing auroral emissions and altering the ionized composition of the atmosphere. Another notable discovery came in 2018 when the presence of hydrogen sulfide clouds was confirmed through spectroscopic analysis. This finding suggests that the chemical processes within Uranus's atmosphere are more complex than previously believed, with multiple cloud layers depending on altitude. Methane at the highest levels, hydrogen sulfide beneath it, and possibly water clouds even deeper. In many ways, Uranus resembles a vast ocean whose great waves appear only rarely, but when they do, they carry astonishing power. It is precisely this slow rhythm that has made the planet easy to misjudge, and for years we believed Uranus had no weather at all. In reality, it does, with brilliant clouds flaring in infrared light, winds moving at extreme speeds, and subtle chemical transformations unfolding in silence, all revealing an atmosphere alive in its own way. And if the atmosphere is already this complex, then what stories remain hidden in the environment surrounding the planet, where its moons and rings drift silently through the darkness? When we move beyond the pale green cloud tops of Uranus and look farther outward, we enter a complex and mysterious orbital system. Uranus possesses a family of 29 confirmed moons, along with a thin ring system so dark that it nearly swallows light itself. The 5 largest satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, contain almost the entire mass of the Uranian moon system. Titania is the largest, with a diameter of about 1,578 kilometers. Oberon follows closely at 1,523 kilometers. Ariel measures 1,158 kilometers across. Umbriel about 1,169 kilometers. And Miranda is the smallest of the major moons, with a diameter of only 472 kilometers. But size alone does not capture their strangeness. Miranda is one of the most unusual celestial bodies ever observed. When Voyager 2 passed by in 1986, the images it sent back revealed a surface that looked like a shattered mosaic pieced together again. Ariel, by contrast, appears younger, marked by numerous valleys and long chasms stretching hundreds of kilometers, and far fewer impact craters than Umbriel, suggesting that it may have experienced internal geological activity or surface renewal in the past. Titania and Oberon, the 2 largest moons, display evidence of enormous fractures, hundreds of kilometers long, possibly formed as their interiors cooled and contracted. Some thermal models suggest that if enough tidal energy once existed, subsurface oceans may have formed beneath their thick water ice shells, though no direct confirmation has yet been obtained. Then there are the rings. The ring system of Uranus was first discovered in 1977 through the phenomenon of stellar occultation, when the light from a background star was blocked multiple times before the planet itself passed in front of it. Unlike the brilliant rings of Saturn, the rings of Uranus are extraordinarily dark. Their reflectivity is below 2%, making them the darkest ring system in the solar system. These rings and moons preserve the dynamical history of the entire system. Their orbits reflect how Uranus may have acquired its extreme tilt, how gravity is distributed around the planet, and how ancient collisions may have reshaped the system over time. And when we look beyond the solar system, we begin to realize something important. Most of the exoplanets discovered so far are roughly the size of Uranus or Neptune. Understanding the moons and rings of Uranus is therefore not simply about studying a forgotten planet. It may be a key to understanding billions of other worlds across the Milky Way. Uranus orbits the Sun at an average distance of nearly 2.9 billion kilometers. It is cold, distant, and difficult to observe. Yet it is precisely that remoteness that turns Uranus into a rare natural laboratory. In this deep cold environment, methane persists in the upper atmosphere, absorbing red light and leaving behind the planet's distinctive green hue. The methane absorption spectrum, observed on Uranus, has become a crucial reference for scientists when calibrating spectroscopic models used to study the atmospheres of exoplanets. If we do not understand exactly how methane, ammonia, or hydrogen behave under different pressures and temperatures, we could misinterpret the entire nature of a world hundreds of light years away. In 2023 and 2024, the James Webb Space Telescope observed Uranus, and the data collected from those observations do more than deepen our understanding of the planet itself. They are also being used to refine the algorithms that retrieve atmospheric compositions from the faint signals of exoplanets. Modern models of planetary formation suggest that planets the size of Uranus formed by first accumulating a rock ice core roughly 10 to 15 times the mass of Earth before capturing additional hydrogen and helium gas from the protoplanetary disk. Yet the precise ratio between rock and ice water, ammonia, and methane in supercompressed states remains uncertain. Every physical parameter of Uranus becomes a variable in the equation of planetary formation across the galaxy. Even the orbit and position of Uranus carry broader implications. If Uranus once migrated through the solar system, its motion would not only have affected its own moons, but may also have helped shape the environment in which Earth itself formed. This leads to an even larger question. If other planetary systems also contain Uranus, like worlds that migrate closer to their central stars. Could they alter the fate of smaller rocky planets within those systems? Observations of exoplanets have revealed many hot Neptunes, planets similar in size to Neptune, but orbiting extremely close to their stars with orbital periods of only a few days. Our Uranus does not reside near the Sun, yet understanding its structure and atmosphere allows scientists to simulate how a similar planet might change if it migrated into a hotter region of space. Uranus is no longer simply a distant and forgotten planet. It is a primordial version of one of the most common classes of planets in the galaxy. That realization changes how we see our own place in the universe. When we observe Uranus through a telescope, we are not merely looking at the seventh planet from the Sun. Love scenario. We are looking at a prototype, a fundamental blueprint for billions of worlds. The coming decade may determine whether Uranus remains an enigma or becomes a foundation for decoding planetary systems across the galaxy. A dedicated orbital mission, an atmospheric probe descending into the clouds, and long-term measurements spanning many years are gradually turning from ideas into concrete plans. If Uranus is a key, then we are standing at the door. For many decades, we mistakenly believed that Uranus was a quiet and monotonous planet. Yet that apparent silence was only a surface illusion, concealing a complex atmospheric system where enormous storms operate on seasonal cycles that last for decades, and where the planet's internal structure differs profoundly from that of any other ice giant. New physical models suggest that Uranus does not suffer from a lack of internal energy. Instead, it appears to function according to a form of planetary dynamics that we are only beginning to understand. From its faint ring system to its moons that carry the scars of violent collisions in the distant past, every component of this world reveals an extreme natural laboratory for studying fluid physics and asymmetric magnetic fields. Recognizing that we were wrong about Uranus is not a setback, but a necessary correction in our understanding. In the cold darkness beyond the orbit of Saturn, this planet is no longer a forgotten object drifting in silence, but a reminder of the universe's endless complexity. The mistakes of the past are what open the door to the next chapter in our effort to understand how worlds form and evolve, reminding us that the truth of the cosmos often lies just beyond what our eyes can immediately see.
Look at the energy fluctuations near the sea ring.
The methane levels are spiking higher than anticipated. We need to recalibrate the sensor array.
Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.